Hello everyone, myself Krishna Pranav, and I'll be presenting you the topic building a better hash function. This is a technical perspective and it's data related to data structures. Introduction to hash functions. A hash function maps variable length input data to a fixed size output known as hash value or digits. In data structures, hash functions enable efficient data retrieval via hash tables with average O of 1 time complexity. Ideal hash functions exhibit uniformity, minimizing collisions across diverse input distributions. Determinism is essential. Identical inputs must always produce the same as output for consistency. Hash functions are foundational in hash tables, cryptographic systems, and data integrity verification. Properties of an ideal hash function. Uniformity ensures that hash values are evenly distributed across the output space, reducing collision probability. Determinism guarantees that the same input always yields the same hash. Critical for data structure reliability. Efficiency requires the function to compute hashes in constant time, O of 1, regardless of input size. Avalanche effect ensures that small input changes produces significantly different hash outputs. Non-invertibility prevents reconstruction of the original input from the hash, enhancing security. Common hash function design techniques. Division method uses modular arithmetic h of k equal to k mod m, where m is typically a prime number to reduce clustering. Multiplication method combines key multiplication with fractional extraction h of k equal to m of ka mod 1, where a equal to root 5 minus 1 divided by 2. Universal hashing selects a random hashing function from a family to minimize worst-case collision scenarios. Polynomial rolling has uses base expansion h of k equal to k naught a per n minus 1 plus k1 a per n minus 2 plus so on until k of n minus 1 mod m. Commonly in string hashing. With manipulation techniques like XOR folding and rotation enhance diffusion and reduce bias in output. Collision handling strategies. Separate chaining stores collider elements in linked list at each bucket, preserving all entries. Open addressing resolves collisions by probing subsequent slots using linear, quadratic, or double hashing. Linear probing uses h of k comma I equal to h dash of k plus I mod m, but suffers from primary clustering. Quadratic probing applies h of k comma I equal to h dash of k plus c1 of I plus c2 of I square mod m to reduce clustering at the cost of potential cycle issues. Double hashing employs a secondary hash function h of k comma I equal to h1 of k plus I of h2 of k mod m, offering better distribution. Analyzing hash function performance. Load factor alpha equal to n by m, n items, m buckets, directly impacts collision frequency and performance degradation. Expected number of probes in open addressing is approximately 1 by 1 minus alpha for successful searches under uniform hashing. Separate chaining method maintains O of 1 plus alpha average search time due to line traversal in buckets. High variance in bucket occupancy indicates poor hash function uniformity and increased collision likelihood. Empirical testing with real-world data sets reveal practical performance beyond theoretical models. Cryptographic versus non-cryptographic hash functions. Cryptographic hashes, example SHA-256, prioritize security. preimage, second preimage, and collision resistance. Non-cryptographic hashes, example, murmur hash, FNV, emphasize speed and uniformity for data structure applications. Cryptographic functions are computationally expensive due to complex bit level operations and multiple rounds. Non cryptographic functions often use simpler arithmetic and bitwise operations optimized for CPU pipelines. Choice depends on use case. Security critical systems require cryptographic strength as tables favor speed. Designing a custom hash function, key considerations. Input domain analysis is crucial. String, integer, or composite keys require tailoring mixing strategies. Prime seed tables reduce modular bias, especially when using division-based hashing methods. Avalanche testing ensures that each input bit affects approximately of the output bits. Mixing functions like XOR, addition, and rotation should be combined to enhance diffusion. Avoiding fixed patterns and symmetries in a function prevents predictable collision clusters. Example: polynomial rolling as for strings. The function computes h of s equal to s naught p of n minus 1 plus s1 p of n minus 2 plus so on s of n minus 1 mod m, where p is a prime base, example 31 or 53. Ordnance rule optimizes computation h of s equal to s naught p plus s1 of p plus s2 of p and so on till sn of minus 1 mod m, reducing multiplications. Choosing p alphabet size minimizes collisions. M should be a large prime to avoid modular wrap around bias. Pre-computed powers of p modulo m enable often substring as queries in rolling as application. Vulnerabilities include as flooding attacks if P and M are predictable, necessitating randomization in security context. Advanced technique, tabulation hashing. Tabulation hashing divides input into bytes and uses pre-computed random tables for each byte position. Each byte is used as an index into its corresponding table and results are XORed to produce the final hash. Despite simplicity, it achieves strong theoretical guarantees of one time and high independence, example, tree independent. Memory overhead is manageable. 256 entries per table into number of byte segments, example, 8 KB for 32-bit input, effective in practice for hash tables where cryptographic security is unnecessary but strong uniformity is required. Evaluating hash quality. Statistical test. Chi-squared test assessed uniformity by comparing observed bucket frequency to expected uniform distribution. Entropy measurement quantifies output randomness. Higher entropy indicates better dispersion. Collision rate analysis across diverse datasets reveal real-world performance deviations from theory. Avalanche criterion testing flips each input bit and measures average output bit change, target 50%. Spectral analysis examines hash value distribution in multidimensional space to detect clustering patterns. Optimizing hash functions for modern hardware. Exploiting SIMD instruction allow parallel processing of multiple hash operations, improving true output. Cache-friendly designs minimize memory latency by reducing table lookups and pointer chasing. Branchless implementation using conditional moves or arithmetic avoid pipeline solves from mispredictions, loop enrolling, and Inlining reduces function call overhead in tight hashing loops. Compiler in strings and assembly optimization can fine-tune performance for specific CPU architectures. Improving Java strings as functions. Original Java string as s of 0, 3, 31, n minus 1, using 31 as multiplier. Alternatives include switch to faster, more uniform functions like murmur as tree in custom as tables. Trade-off. Backward compatibility versus security and performance motivates gradual adoption in JVM uniforms. Research challenges. Energy efficient caching is critical for IoT and embedded systems with limited computational resources. Formal verification of hash function correctness and security properties remain a challenging open problem. Machine learning models are being tested to learn optimal hash mapping from data distribution. Quantum resistant hash functions are emerging to counter future threats from quantum computing. Thank you.